Coming up, Cosmic Queries, the Black Hole Edition. Chuck is going into my black hole bag.
It's dark in there.
To get questions. We've got your questions on that very topic. So, YouTuberverse, check it out. Coming up now. This is Star Talk. I'm Neil deGrasse Tyson, your personal astrophysicist, and I'm with Chuck Nice, co-host.
That's right.
Chuck, and we are recording live from my office at the Hayden Planetarium of the American Museum of Natural History right here in New York City.
Better known as the Cosmic Crib.
Oh, the crib. Welcome to the crib.
Welcome to the crib.
That was high currency when I was in college.
Yeah.
I hadn't heard anybody use it anymore.
No.
Yeah.
Nah. It's kind of it's
just very dated.
It's very dated.
Yeah. But it still sounds cool. The crib.
It does. Yo, what's up, man? I'm just
to the
chilling
crib.
in my crib.
See, that worked. That still works. That still works. For anybody over 50. So this is actually part 2 of Cosmic Queries we began last time.
That's right.
Because we had sufficient questions to populate 2 Cosmic Queries on black holes and dark energy.
People love it.
I know.
People want to know
How could you not?
lot about the dark energy and black holes.
And since we don't know anything about dark energy, I want to know about it too.
That's right.
All right. All right. Give it to me. What do you have?
All right. So we are going to start with a Patreon patron.
As is our habit.
Absolutely. So this is Chris Hampton. And he says, hey, Hawking radiation states that a black hole will eventually evaporate completely because it's releasing small amounts of energy / mass over time. But wouldn't the black hole's consumption of matter overpower the radiation, making the black hole grow instead of evaporate?
Yeah, good. So if you have an isolated black hole,
Right.
it's not consuming matter.
Right.
It's nobody there to eat.
Exactly.
You have to come embarrassingly too close to it for it to tidally distress you and capture you.
And now it's good, right.
And you have to be moving not too fast, otherwise you'll just whiz by.
Right.
So the black holes are not some voracious vacuum cleaner that sucks up everything it sees.
I'm so hungry. Right. That's a
that
tiny
they
black
sound
hole.
like?
That's a little black hole.
I'm so hungry. And the big black
There's supermassive black holes are like, feed me. You know.
It is funny, this voice frequency thing. Like, you never have a high frequency voice selling a truck.
Right. That's true. Which now I want to see Mike Tyson actually sell Dodge Rams. Just like,
That's right. It's Ram tough. Dodge Ram. Okay.
Because he is a tough guy.
He's a tough guy.
The question whether that will compensate
Exactly.
for the voice.
Exactly.
Plus, the voice of God is never high pitch.
No, it's never just like, hey guys.
Hey guys, I think I'm going to smote you today.
Oh, see, now I wish Michael Jackson was alive to be the voice of God. Just like,
You're very ignorant. You're very ignorant. I don't like that.
Stop it.
Exactly.
Well, send a tsunami.
Thou shalt not lie.
all right, okay, there you go. So, this information that it consumes, if it's by itself,
it'll just evaporate. Yes, clearly, and as correctly surmised, if it has a food source,
right,
it's just going to eat, and the Hawking radiation will be insignificant,
right,
of a loss relative to what it's eating.
Gotcha.
But eventually, all black holes will have eaten anything they can eat,
right,
in their refrigerator. At that point, then it'll slowly start evaporating at a higher rate than it was gaining mass.
Gotcha.
So that's how that plays out.
And the evaporation, though, if nothing can escape, what is actually evaporating?
Good question. Mm-hmm. Very nice.
Yes.
Evaporation we're using the term loosely here.
Okay.
All right. So what's actually happening, and it's brilliant. It's beautiful.
Okay.
I have to say, it's beautiful.
It's beautiful.
It's beautiful.
So what's going on is a black hole's the gravitational field in the vicinity of a black hole is so intense,
right,
that it will spontaneously create matter.
Holy crap.
So the energy density, because E equals mc squared, if I have matter, I can turn it into energy. That's what nuclear bombs do.
Right.
But if I have energy, I can turn it into matter.
Right.
The energy density in the field of black holes is so intense, right outside the event horizon, it will create particles
Wow.
out of the gravitational energy density of the field. Now watch. Here's the spooky part.
Okay.
Okay. These particles were not inside the event horizon. They're created outside the event horizon.
Right.
Okay. Now watch what happens. When anytime you make particles from energy, you make two particles every time.
Okay.
Matter and antimatter pair.
Wow.
I don't know if you knew that.
Oh.
Yeah. Okay. And they will travel in the exact opposite directions from each other.
Gotcha.
That means one escapes, the other goes right back on in.
Right.
Okay. So, but the one that escapes forever.
Right.
If you measure the mass of the black hole, it is now less by the mass of that one particle that escaped, even though these particles were created in the gravity field of the black hole itself.
Nice.
So it's giving of itself just from the energy density of the gravitational field. It's really a remarkable fact.
That is remarkable.
Right.
Wow.
Yes. And so Hawking figured this out, okay, and then concluded if this keeps up, the whole black hole is gone.
Right. At some point.
Right.
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 That's amazing. Mm-hmm. So it's
And in fact, the smaller the black hole, the faster it will radiate.
Gotcha.
Okay? It's a surface area thing. It has
Here we go. Up. Surface area alert.
Because we have a whole show on
Yes,
surface
we
area.
do.
It's so the larger the object, let's say it's a sphere, the larger the object, the less surface area it has relative to the volume.
Right.
Okay? And the smaller you are, the more is your surface area relative to your volume. This is why children and babies should not spend too long in the hot tub.
Right.
Because their connection to the hot environment is way more devastating to their body than it is if you're bigger.
Right.
That's all. So as the black hole gets smaller and smaller, the rate of evaporation increases because its surface area gets larger and larger compared to the volume that's inside of it.
Wow.
The surface area of the event horizon. And the intensity of the energy goes up. And so its very last gasp is a pulse of light of the highest known energy, which are gamma rays.
Wow.
Okay?
That's pretty cool.
So the original paper written by Hawking talked about bursts of gamma rays in the universe from black holes evaporating in their very last gasp. And then we saw gamma rays in the universe with a telescope after the data were declassified. We had a telescope launched in the early 70s, trust but verify, right? Oh, let's sign the test ban treaty, no nuclear tests in the atmosphere, anywhere
Right.
else. We said, okay, Ruskies, but we're going to put up a satellite that'll look for gamma rays just in case you don't fulfill the treaty. And we started detecting gamma rays like every day. It's like, can we get some ground truth on this? Checked other satellites, no explosions anywhere. A whole brand new field of astrophysics was pried open by accident because we're trying to verify.
Because we don't trust the Russians.
Because we don't trust the Russians. And these,
I don't know why we wouldn't trust the Russians. They're such good people. I want to be friends with them.
good people all around.
That's right.
So those gamma ray bursts, are they these black holes? No, because you can look at the properties and it's not.
Right.
Yeah, okay.
Fascinating.
Yeah.
Man, thank you. Hey,
Yeah.
hey, Chris, thank you for that. That was
All right.
really a nice trip, man. I love it. Okay.
All right, next Patreon question. Go.
All right, there we go. This is from Oak Steele's funny fake one. Okay, you're just screwing with me. I know that now. All right.
All right.
I don't think I have a proper question here. You don't have a proper name either. But can you
Chuck
please
is making people feel good.
but can you tell me about the singularity of a black hole? Like, whatever you know about it, thanks in advance. Okay, there you go.
I'll tell you what
At
we
the
know.
center of a black hole is supposedly a singularity.
I'll tell you what we know.
Go ahead.
All right. The collapse of a thing to a black hole, we take it to a black hole because there's no known force in the to us in the universe that would prevent it. And if you do the math, the gravity is so severe that it will collapse to get denser and denser and denser until it is infinitely small. which would make it infinitely dense.
Correct.
Because density is mass divided by a volume. Grams per cubic centimeter.
Right.
Okay. Pounds per cubic foot. These are statements of density. So if you have a certain amount of mass and the volume goes to 0, what happens if you divide by 0?
Well, you get an error on my calculator.
Okay. Before you get to 0, the numbers get astronomically large.
Right.
So you actually get to infinity. So it is infinitely dense. And so can you even have that in nature is the question.
Wow.
We don't know.
Right.
But invoking only Einstein's general theory of relativity, you get a point of infinite density.
Right.
String theorists came along and said, we got this. It's not infinite density. There's strings, and there's another thing going on in the universe. That's why you bring in string theorists. Okay? We ring the bell. They come in and say, we got this. You needed extra physics on top of general relativity to understand the singularity. And once you did that, they say, hey, this is good to us. Let's think about the singularity that began the universe itself. The Big Bang singularity.
Right.
So this gives you access to previously mysterious elements, taking Einstein's theories to their limits. So if there's no singularity, there could be something else. But according to Einstein, that's what you get.
Gotcha.
Yeah. But we're admitting that Einstein's theory is incomplete at the singularity. We're waiting for a bigger theory to come along to replace it.
Right. Okay, that's pretty fascinating stuff, man.
Yeah.
I just love it because, that makes sense. It's like there's a single point.
And how did you even wrap your head around
How do you wrap
that?
the right?
Right.
Yeah, that's pretty wild.
We're awaiting some new physics, or we got to successfully wrap our head around something infinitely small and infinitely dense.
See, so what? See, I get the infinitely small, infinitely dense. I mean, I see.
And that's at the center of the black hole.
That's at the center of the black
Right.
hole. And so if you
if the black hole's rotating,
right,
then it's not a singular, it's a donut.
a ringularity. Nice.
Oh, I like that word.
I learned it from my son. I got to be honest.
He said ringularity?
Yes.
He
So,
came up with that word?
I don't think he came up with it, but that's what he told me it was.
That's a
and
good
I told
word.
him that it's not a
I'm gonna talk to
singularity. I said it's a singularity. And then he went to Jan 11 and she said, yes, it's a ringularity. I was like, I hate you, boy.
Just someone that wants to start an astrophysics club
Yes,
in his middle school?
Middle school, yes.
And not a comedy club.
Not a comment. Thank you, Jesus.
Man,
I mean,
is that a burn?
I don't care. I'm just happy that he does not want to go down this path. Yes, I'm serious. Be an astrophysicist and write some books and take care of your father. That's what I'm saying.
That you want him to do with you.
Yeah,
All right.
there you go.
All right.
Yeah.
Okay.
But anyway, yeah, that's pretty cool. So
This is messy. I have a better idea.
for what?
Okay, give
My
me these.
strips? Okay,
Here,
you're
give me-
taking all these papers.
Wait, you hold it. Hold on to them.
I'll hold the papers.
Okay. I have a black bag here.
These are all my questions.
This is an actual black hole.
Okay.
Okay. Because first it says it.
It says a bag. Oh, my God.
I got all kinds of stuff in my office.
Oh, that's hilarious.
Okay. And as all
So
black
it's a
holes.
black bag.
Okay. And as all black holes do, they'll watch you as you fall in. Okay.
Oh, that's hilarious.
Okay. So this is my black hole bag.
It's a black hole
It's
bag.
got a drawstring. Okay. So put them in here.
Okay, I'm putting all the bags, and now I'll just pull them out. Oh, now listen. You get your question answered
At random.
At
Okay,
random.
go on.
Okay, I'm going in. Wait a minute. I can't stop. I just fell in a black hole.
You know, I did an experiment with what was inside of here.
Oh, okay.
You just did that experiment.
Exactly. All right, here we go. Pull one
All
out.
right.
All right. Wow. Here we go. Chris Wakefield wants to know this. Hi, it's Chris. It's a philosophy question. Since every galaxy we observed so far has had a supermassive black hole at the center of it, and theoretically a black hole could be turned into a wormhole, what if they were used as save points, like in a video game, across space and time for a creator of sorts to get across galaxies more quickly to create what we know as space? Just a weird thought I had. All right. So, Chris, number one, please give me the number of your weed dealer. That is the first thing I would like. Because this is some good stuff. All right. So, anyway. So, basically, what he's, the idea.
But I think what he wants is because black holes and wormholes are related and may be related.
Okay.
And he wants to know whether there's some, I might be exaggerating his question,
Okay.
whether there's some intergalactic highway system
Yes.
that connects one galaxy to another.
Yeah,
across the universe.
Right.
Through these black holes.
Through these black holes. In other words, like it's, kind of like what's that city? Milwaukee. Where they have the
no, it's not Milwaukee. You're talking about
Minnesota.
It's
What city is
Minnesota's
that?
the name of the state.
I'm saying, but it's in Minnesota.
Minneapolis.
Minneapolis, that's what I'm trying to think of.
Yeah, so
Where
Minneapolis-
they have you walk you never have to go outside.
I mean, when it's 40
It's
below.
really cold
When it's 40
you just
below.
walk between buildings.
Right. And there's Skyway News. It's called Skyway. I think it's called Skyway.
I think it is called Skyway.
And to me, when the first time I saw it looked like an ant farm.
Oh, that's funny. The human habitrail.
Yeah, I didn't
That's
want to. I felt uncomfortable in that. I said, "This is we are in someone's zoo."
Protect
here.
the queen. Protect the queen.
Right. So each buildings are connected, so you never have to go outside.
Yeah, exactly.
So here's the thing. Nobody would love the idea more than I would. Here's the thing. If a black hole, which only eats things, is a portal to a wormhole, the other side of that wormhole can't also be a black hole.
Right. It has
Because
to
then
be
you wouldn't be
shoving things out.
That's called a white hole.
Oh, really?
Yes.
Now, see, why the white hole got to be given and the black hole got to be taken? That's what I'm trying to figure
Chuck,
out.
not every reference is bad.
Okay.
To black things.
All right.
Okay.
Okay.
All right.
Do we have
The Black Plague.
a kiss my black a kiss my black hole? All right.
You just said you were born too late to join the Black Panthers.
Exactly.
That's all.
Right. So is there really a white hole? That's a white
Black
hole.
Panthers, that's a double reference back. The Black
Yes, it
Panthers,
is.
the group from the Civil
From the
Rights
Civil
Movement.
Rights. And
Not the movie.
That's right.
Right. I'm just
And the
saying.
guy that uses vibranium. So
Yeah. So where were we?
We were talking about
Yeah.
the fact that there is something called a white hole. There,
Yes. So something called a white hole.
And that you didn't just totally
which would
make
be
that up.
I did not totally make it up. And this was explored in the 1970s.
Okay.
When the mathematics of black holes were coming to maturity. And someone posited, well, if you have a black hole, what's on the other side? It would be like a white hole. I mean, why not? Where
Right.
everything only comes out.
Right.
Then how would you connect them? With a wormhole.
Nice.
So you get 3-for-1
Right.
deal on that. And then you can ask yourself what a white hole would look like in the universe. So in the 1970s, we said, if this is what a white hole would look like, let's check the data. Let's go to the universe.
Right.
Nothing in the universe resembled it.
Gotcha.
Not even quasars, which are intense emanations of light from the distant universe in a very small volume. So we abandoned that.
Okay.
So if you could, I don't mind wormholes connecting the galaxies. I just don't see how you would invoke the black hole to do that.
To do it.
That's
Gotcha.
all right. But
Excellent.
great question. We're going to take a break?
Yep.
Before we get lost in the black hole bag?
Exactly.
And when we come back, more cosmic queries, black holes and dark energy when we return. We're back. Star Talk, Cosmic Queries, black holes, dark energy.
Yes.
We had so many questions. It's part 2.
This is part 2.
And for this part, I have my special
Black hole bag.
black hole bag.
That's hilarious.
It's just black hole.
That's right.
All right. And I don't know why they got little Google eyes on it, but okay. So
And
reach
so
in.
I'm reaching in the black hole, and okay, it just seems to be. Wouldn't it be funny if my hand just came out on the top?
that
here?
would be really freaky. That'd be a wormhole.
Like the wormhole black hole bag.
All right.
All right. Hey, this is Mike Rush from Facebook, and he says, if nothing can escape a black hole, including light, and nothing can move or travel faster than light, how is there massive jets of X-rays coming off many supermassive black holes? Wouldn't that mean that these particles / waves have been accelerated beyond the speed of light? Ooh,
There's people paying
I'm
attention to the
telling you,
news.
these
People reading
are
this stuff.
top. They're on top of this.
On the game. Why are you ripping up the boy's question?
I was trying to make it for just emphasis and
Emphasis?
Yeah.
Okay.
I was trying to be emphatic, but instead I tore his
Okay.
question.
You know what does that really well? Are belts. Have you ever done that with a belt?
Of course, yes, snapping a
You
belt.
have smelt that time. Like this, I'm talking
You
about.
take a belt and you snap. That's how I keep
the
my
best thing.
children in line.
No, but what's good?
I don't
do
ever
you have
hit
a
them.
belt?
I just take the belt. And
Do you have a belt?
I have a belt, but it's
Let me see,
not
what kind
that
is it?
Oh no, it's leather.
Is it a leather belt? Give me.
Yes.
Give me.
Let me take my
I'll show
belt
you.
off.
I just want to show you something.
Okay.
Just leather? Yeah, that'll work.
This is leather.
Okay. Okay, so watch.
There you go. All right.
So this, I just want to show
For
you
those
this.
of you listening, Neil now has my belt. My pants
Okay.
are down around my ankles.
Okay, so
Now,
here it is.
Neil has my belt.
This is just, I just want to show you, okay?
Wow.
You see that?
Yes.
Okay, so it turns out
Right.
that sound
Wow.
is only made at the last instant that these make contact.
Okay, that makes sense.
Okay?
Right.
But if you put your finger there.
No, I'm not doing
do
that.
I promise. I
Oh,
promise. I promise. Well,
what kind of trick is this?
We go way back.
All right, here we
Chuck,
go.
Okay.
I'm going to trust you. Here we
Okay,
go.
so, well, just again.
Okay. Whoa! I'm not leaving my finger in there.
Okay, now put your finger in.
Oh, come on now.
Come here.
Go ahead. Oh, look at that. Oh, my gosh.
See that?
Look at that.
You didn't know about
I
that?
had no idea.
So you can scare people with it,
Right.
but really
And nothing.
it doesn't.
That's amazing.
Because it's only the
Like a kid. I'm so easily impressed by stuff. I'm like, oh my God. It doesn't hurt.
You didn't know about that?
Yeah, but see, listen, I'm black. That belt represents a
A
lot.
whole lot of butt whooping.
That's
Ass
right.
whooping. All right.
Oh my God, I've never seen that. I can't wait to go home and do this to my 5-year-old. Now put your finger in there. That was awesome.
Okay.
Go ahead.
All right. You can put your.
I can put my
Oh,
belt
while
back.
I'm answering.
Yes,
So
go
what? So the question was. Oh, about the. Okay. So
So
here's,
these supermass, these X-rays that are
Here's what
coming
happens.
off of these supermassive
you ready?
black holes.
Here's what happens. You have all this matter trying to get into the black hole,
Gotcha.
not on purpose.
Not on purpose. Right.
Trying to not get in the black hole.
Right.
All right. Most matter that falls towards a black hole is not falling exactly on line with its location in space.
Gotcha.
That would be unusual.
Right.
Typically, it would just fall off to the side, one direction or another. Okay?
Gotcha.
So it turns out the system, the rotating system, as matter tries to come in, it'll miss the black hole, but then it'll get pulled into orbit around it.
Gotcha.
Okay? And so now you have this circulating matter.
Right.
And we have a term for it. It's called an accretion disk.
An accretion
It's
disk.
accreting
Hey.
material. All right.
Nice.
And this accretion disk feeds the black hole. The innermost part of it goes unstable in its orbit, and then it spirals down, and that's lost forever.
Right.
Okay. But in order for all this matter that used to be out here
Right.
to end up here, there's a lot of gravitational energy it has to release to do that. So let me just a little more TMI on this. You ready?
Good.
All right.
Go for it.
If I just drop something towards Earth, what happens to its speed?
It
Increases.
accelerates.
It accelerates.
Right.
Right?
Yeah.
Okay. All right.
9.8 centimeters per second squared or something.
Meters per second.
Meters
Of
per
course.
second
Yeah, you
squared.
got the significant
Yes,
digits.
exactly.
Okay. All right. So it's 900.
Centimeters per second. That's funny. Go ahead. Meters per second.
980
squared.
centimeters.
Right.
All right. So here's the thing. So to get from some distant place to the black hole
Right.
and then stop moving,
Right.
where does all that energy go? All right. And what I'm saying is any matter that's trying to get to the black hole from far away is going to have to release that energy if it's going to land where the black hole is.
Right.
And so, since most of it misses the black hole and goes to the side, you get this disk. And so you have this disk of material all trying to get in, and there's friction between the inner layers that rotate faster than the outer layers. There's material hitting it, and then again it's stopping because it hit it, but that's a collision with it. And we have bright spots that show up on these accretion disks.
Right.
That's an active place.
Yeah, that's
And if you're a disk and you're trying to radiate, you can't radiate through the disk because there's disk stuff there.
right.
Where's the only place that's free and clear to spit up material and energy? Above and below the disk.
Right.
Okay?
Right.
So
That's great.
you have this thick accretion disk and it's basically empty on the top and bottom.
Right.
So all the energy that is trying to get in and can't will get released in the opposite directions, and you get generally you get two disks
Right.
coming out. on the poles of this accretion disk.
That's beautiful.
You get two jets
That's
coming out at the poles of the accretion disk.
That's amazing.
Yeah, it is completely
And those
amazing.
are all the pictures that you see of the black hole with the jets
With the
spewing
jets
out.
coming out. And this is material that never got into the event horizon.
Right. So it's not that it's escaping the black hole. It never made it in.
It never made it there in the first place.
It's actually the dejected, non-party going club people that were not allowed into the
Rejected
club.
from the velvet rope.
Right. Exactly. They couldn't get past the velvet rope.
They weren't just walk away. They got ejected.
Exactly. That is wild.
Yeah. So there it is. And that's why. So, but you only get it if you have an accretion disk.
Right.
And if the accretion disk is really thin and sparse,
Right.
then the energy can go kind of in multiple directions. You won't get these really strong
Like
jets.
strong plumes that come
yeah,
off
you won't
the,
get the
top
the
and
full
bottom.
jet. And what it also has a way of doing is the term is collimates. So it actually makes everything come out only in that one direction, like in a pencil beam.
Nice.
All right. So if you don't happen to be in a sight line to it,
Right.
it's not going to be very bright to you.
Exactly.
So there's some galaxies that are supremely bright. Mm-hmm. And it's because we think that this jet is actually facing directly towards you. Wow. With all this energy focused down into this jet.
That is amazing
There you go.
stuff. What a great question.
There you go.
Nice.
All right.
Excellent.
Well,
All right.
hang on.
Look, mix it up.
Okay.
I'm going in the black hole.
All right.
And I'm pulling out. Here we go. This is Kenoda Bradford. Kenoda once. Oh no, I'm sorry. Keonta Bradford.
How can Kenoda become Keonta? Damn. Chuck.
Because I just made it that.
All right.
All right, Keonta wants to know this. If photons have no mass, how does the gravitational force of the black hole pull in the photons?
Ooh.
What a great question.
Oh, I can answer that in two ways.
Okay.
Each of them kind of mind-blowing.
All right, good.
Are you ready?
Yes, please.
Okay.
Excellent.
So the first one is simple.
Right.
Energy and mass are the same.
There you go.
Two sides of the same coin.
Right.
You can plug the energy of the photon into E equals mc squared equation. That's the E.
Right.
And divide that by c squared, and out the other side comes the mass.
Right. And the cool thing is, and that makes sense. That's why you have an equal sign there.
That's what equal sign.
That's what an equal sign is.
That's how equal signs roll.
Exactly.
When you're doing a calculation, equals mc squared is the same as m equals e divided by c squared.
Exactly.
So c is the speed of light squared. So you take your energy of the photon divided by c by light squared. That you get a mass out of that.
There you go.
So now you can think of the black hole attracting a mass.
Right.
And it'll attract it in exactly the way. It'll attract the photon in exactly the way it would a mass of that amount. Okay. All right.
I love that.
Okay, but wait, that's not the more interesting answer.
Okay. Well, you had me.
Okay. A photon
Okay.
travels along the fabric of space-time at all times.
All right. Give me a second, man. Just wait a second, please. Give me 1 second. A photon travels along the fabric of space-time
Yes.
at all times.
Yes.
So therefore,
Yes.
it is not traveling at any time. Although it's traveling in time and space.
You went a little too far on that one,
went
Chuck.
too far. Yeah.
Okay.
Okay. I'm not
Okay,
as
well,
artful at explaining
here we
this.
go.
So
All right,
my brain is
So here we go.
go for it.
So here we go.
There you go.
Holding aside the fact that because the photon goes at the speed of light, it has no time. Let's hold that aside because time has slowed down so much, it's actually stopped for a photon.
So photon has no time at all.
It has no inner clock. So the instant it is emitted anywhere in the universe
Okay.
is the same instant as it is absorbed by your detector at the business end of your telescope.
To it.
To it.
To it.
It knows nothing of the journey between being formed and being
All
and
right.
hitting something
Okay.
and getting absorbed.
Okay, wait a minute a second.
Okay. By the way, I say about my photon, if you're on the beach sunning yourself, there's a photon from across the galaxy,
Right.
travel the whole galaxy and lands on your buttocks.
Right.
You've heard of the famous experiment conducted by Sir Arthur Eddington?
Oh, of course. My favorite. Yes. Sir Arthur's famous experiment.
Artie.
Yeah, Artie. Oh, Artie.
So 4 years after Einstein put forth his prediction
Right.
that gravity bends space and time. Arthur Eddington, during a total solar eclipse, conducted an
Yes,
expedition.
I know this story.
That's why I knew you knew it. To measure whether light coming by the edge of the sun,
Right.
whether its path was bent. And the way you
Exactly.
do that is you get a map of all the stars during a solar eclipse, because you can't see the stars otherwise,
Right.
and get their exact position on the sky.
Yes.
Then wait 6 months later and take a picture of that same part of the sky. 6 months, the sun is not in the thing.
Right.
There it is. And then you compare their positions.
Right.
And he found that the stars closer to where the sun was, their position had shifted.
Wow.
And so this is the bending of starlight around the sun.
So cool.
Okay, so here's the point.
Go ahead.
The starlight never bent. The photons always took a straight line. That straight line was bent in the fabric of space itself.
Exactly. Which means.
The photon knew
No,
nothing
right,
else
right.
but to take that path.
Wow. So the actual curvature of space-time itself is the surfing. That's what the photon is surfing.
Yes.
The actual curvature of space-time itself.
Yes.
Holy
That is why.
I'm sorry. My God.
Holy poo-poo.
Holy poops.
Okay. So.
Oh my God. That's amazing.
So in that context, the black hole isn't sucking in the photon.
No.
The photon is just following the curve.
The photon is on a skateboard in a pool.
Yes,
That's
skateboard.
what's happening.
It's skateboard.
on a skateboard
It's
in
skateboarding.
a pool, and it's just following the dip of the pool,
Yes.
man.
There you have it.
Dude, that is amazing.
Yes. Photons do that.
That's awesome.
Yes.
Oh, that's so awesome.
Yes. So light technically never curves because that is a straight line to it.
Wow.
To it.
Wow. That
So
is
so in other words, let's say the path came around the path came around,
Right.
And you stand here,
Right.
and look straight in this direction. You're seeing this spot
That's right. That's what you
because space curves.
That's right. That's amazing. That is so cool.
So as far as space and the photon is concerned, they're just going in a straight line.
Exactly. Oh my God, that's so cool.
Yeah.
That is really great.
There you go.
That's good stuff right there, baby.
That's some good shit.
I don't even want to finish the show. Let's go home. I'm good.
We got to take a break. Coming up, yet another segment of Cosmic Queries, Black Hole Dark Energy Edition on Star Talk. We're back. Star Talk, Cosmic Queries, Black Holes. I can say it right. Black holes.
Black holes.
Black holes and dark energy.
That's right.
I got to add something to my answer.
About.
But
right.
you were so...
Yeah, that was it's good stuff.
Can you handle more?
I'm not sure. My head might explode. It's great, though.
Okay.
Go ahead.
The experiment that showed that light bent coming around the sun in 1919.
Right.
Okay, 4 years after Einstein had his idea in 1915, published in 1916. So you might see both of those dates, but referring to the same ideas.
Right.
So he predicts that space will curve in the vicinity of strong gravity, or any gravity, but you want to be able to measure it. So you want a strong gravity source like the sun. So watch. It turns out, if you plug the energy of the photon into equals mc squared and get a mass, and then predict what the curve would be, you get Newton's answer to that question.
Wow.
You don't get Einstein's answer.
Okay.
In fact, Newton, that's ordinary gravity. It's a mass and a thing.
Right.
Okay?
That would be the rubber sheet.
No, we're not yet at the rubber sheet.
We're not even at the rubber sheet
No, Newton doesn't know anything about rubber sheets.
Right, okay.
It's just, I'm a mass, you're a mass, we attract each other.
Right,
Okay?
okay.
So even though it would have never been measured before, the curving of light,
Right.
it had to curve by the amount predicted by Einstein.
Absolutely.
It can't have just been curved light. So you will see news accounts remembering this experiment say, and the light bent around the sun, proving Einstein. No, that just proved that gravity, the photon responds to gravity.
Exactly.
Okay?
I get to what you're saying now. Right.
Okay?
Yes.
So when you invoke Einstein's full-blown general theory of relativity equations, you predict twice the deflection
Gotcha.
of the beam of light than a standard calculation with Isaac Newton. And the measurements made by Sir Artie,
Artie, our boy Artie.
and his measurements recovered that full factor of 2 difference
There you
between
go.
what you would have measured. Wow. So the problem is no one had measured the curvature of light before.
Right.
So it gets bundled together with what would have happened if the light curved but was not as big as Einstein's number.
Exactly.
It would have just been, Newton, your light is also curving.
Right,
Yeah.
exactly. Because
Newton didn't know anything about equals MC squared.
Exactly. So now it's just like big object, okay, or
Yeah.
mass
Right.
attracts, and so now that's why you got the curve.
And you get the right. So we would have
That's
been cool
it.
with
We
that.
would've been cool with
It
that.
was just
I
cool.
gotcha.
It would have curved because the gravity pulled it.
Exactly.
Whereas Einstein, in the fabric of
In the fabric of
space-time,
space-time.
when you run the math on his equations, you get a factor of 2 greater than Newton.
Which
There you go.
Oh my God, which is right, exactly. So that's amazing, and that there shows you that it's the fabric of space time
Yeah.
itself,
Rather than just gravity pulling on.
on something. Oh my God, I love science.
Space tells matter how to move.
Right,
Matter tells space how to curve.
nice.
There you
Sweet.
go.
There you go, baby.
That's a quote from John Archibald Wheeler, a student of Albert Einstein. And I met my to-be wife in his relativity class.
Oh, sweet.
Yeah.
All right, let's move on.
Next question. Got to go to our black hole bag. Here we go.
Into the black hole bag. Pulling out. All right. Hey, Fernando Rodriguez wants to know this. Is it possible that
He
dark...
could be from Hackensack. It's just,
And then
Fernando
it's just-
Rodriguez.
right, then it's just Fernando Rodriguez. All right. I like Fernando. I'm Fernando Rodriguez. It's so very good to meet you.
That's the Puss in Boots.
Yeah,
from,
I was about to say, perhaps you know my friend Kitty Softpaws. All right, here we go.
who was the actor? Who's
That's
voiced
Antonio Banderas.
Antonio Banderas.
That's
That was
right.
one of the funniest characters in
I love it.
all of Shrek. Okay, go on.
Okay, is it possible that dark energy and dark matter are stuff permeating into our universe from another nearby universe, and that our matter and energy is being permeated into another universe? Here's the caveat: via black holes.
So, I mean, just think about it. Hold off on dark energy for a moment, because that's just everywhere, and it would not lend itself as well to this expectation as dark matter would.
Okay.
Okay, so dark matter is a source of gravity about which we know nothing.
Gotcha.
It's not black holes. It's just gravity out there. We don't know what's causing it.
Right.
Maybe it's some new particle. We've got top people looking for new particles.
Nice.
Particles that don't interact with you in any kind of way, don't care about you. So it could be just another sort of coexisting state of matter that we have to learn about. All right.
Gotcha.
What did you know this? I don't know if you knew
Go
that
ahead.
light is trapped within our universe. It can't get out, but gravity can.
That's wild.
Yes, isn't that interesting?
That is very
Yes,
interesting.
and I never took a full up field theory course in graduate school where I would have learned this. So I'm describing this to you because this is what people who I trust and who are experts have told me.
Okay.
Not because I did the calc. Mostly the other stuff I talk about here, I've done the calculations.
Gotcha.
Okay. But the things I haven't, I'm just trusting them.
Okay.
It's a field theory course. All right. In it, the properties of gravity are such that it is not contained within our universe.
Okay.
So if there's a parallel universe, it in principle could feel the effects of gravity in our universe. Well, then so would the opposite be true.
Right.
All right. So if that's the case, maybe there's a hunkering universe out there, because 85% of the gravity of our universe comes from what we call dark matter.
Right.
85%.
Wow.
All right. So we are just blips on a, we're froth on the waves of the ocean. all right?
Exactly.
So perhaps there's a hunkering galaxy, a hunkering universe, 6 times the mass of our. Actually, it would have to be more than that, because to come out of the universe, it has to be even stronger than the ordinary gravity you'd feel within the universe.
Okay.
It's because it's coming out in another dimension.
Right.
All right. So, in other words, if you scream to someone, your voice dilutes as it spreads out
Right.
by a rate we can calculate. Now, suppose you're also screaming into another dimension.
Carol Ann. Mommy. Mommy. Carol Ann?
That's exactly what that. And he's like, where's that? What? Okay.
Turn the channel. She's in the TV.
So if you're screaming, then the energy you need to have strength going to that extra dimension and still matter to wherever it's headed, it's got to be much bigger than just went into your own dimensions here. So that's what I'm saying. Every dimension you add, it dilutes faster. Let me put it that way.
Okay.
Okay?
Gotcha.
Like, for example, if I'm sending marbles down a one-way path,
Right.
there's no dilution.
Right.
Because all the marbles
They're
I
just
start
rolling down
the path.
That's it.
Now, if I spread it out like this in a fan, now the marbles will dilute into a fan.
Right.
Okay.
Okay.
Mathematically, they'll dilute as 1 over r. Okay.
All right.
Now, if I over 1 over the distance. Now, if I dilute it into a cone, they'll dilute like 1 over r squared.
Gotcha.
As does light and as does gravity.
Gotcha.
If I now dilute it into a higher dimension than that,
Right.
you need it'll dilute like 1 over the 4th
Gotcha.
power.
That's funny because you went from flat to 2 to 3-dimensional.
Right. And
Gotcha.
so the higher add a dimension, you need that dimension to get to the other universe.
Gotcha.
All right. So the gravity would have to be like that much more powerful.
Okay.
But suppose at 12 times the mass of our universe, or 100 times the mass of it could be their gravity seeping into ordinary mass with ordinary gravity, seeping into our universe. And since we can't see the origin, which is a mysterious
like,
thing.
what is this?
That
is so wild.
It's mysterious.
That's wild.
That's right.
Oh my God, and
right.
it makes so much sense though.
Well,
it really makes so much sense.
Right. And here we are trying to touch an elephant that's not even there.
Exactly.
Right.
That is cool.
So I'm all in for that. That's the solution I want.
I love it.
Because that'd be evidence, indirect though it was, of another parallel universe to us.
That's so wild.
Right, because you know who's looking for the new particle that it could be? Particle physicists.
Right.
So their hammer's looking for nails.
There you go.
Right.
That's it.
So I'm not any of those hammers. I'm looking for whatever's out there.
Right.
I'll take any of it.
Fantastic, man. That's good stuff.
Yeah, no, it's a really fun concept.
That's got to be like the cutting edge frontier of all physics.
And just for reference, not that I think everyone got that example, but let me give a simpler one just in case you want it.
Yeah, I mean, I got it, but
If
go
we-
ahead. It was a good example
If
as
we
far as I'm
live
concerned.
within a sheet of paper,
Right.
And that's your whole world.
Right.
But you're a three-dimensional person looking at we poor creatures, and you have a hollow sphere. And we might have done this on another show.
Yes, we did.
If I drop that sphere, pass that sphere through your sheet of paper,
Gotcha.
how will you describe that to your other scientists in the sheet of paper? Well, first there's a dot.
Right. And then the dot
That becomes a circle. The circle gets bigger and bigger and bigger, and then it hits a maximum point.
And then we started closing
and then
up
closing
again.
down, and then it ends as a circle. It disappears.
Nice.
Who knows where it went? I don't know.
Right.
Where you just passed a sphere through us.
Right.
So there could be higher dimensional things influencing your space environment that it's the stuff of legends and lores and that sort of thing.
That's cool.
Yeah.
Wow. All right, back to the bag.
Let's do more.
More black holes from the black hole bag.
All right.
Here we go. Mm-hmm. All right, this is Jackson Welch.
Mm-hmm.
And Jackson Welch from Instagram wants to know if a solar system further from...
Wait, so people can send questions to us from all platforms?
From everywhere.
Yeah, okay, good.
Yeah, we're everywhere,
There's
man.
Instagram,
That's
IG.
right. And he says, if a solar system further from the black hole of our galaxy has a planet which inhabits intelligent life, would time be faster on that planet relative to ours? Also, if their planet had life develop at the same time as ours, might they be more advanced due to the relative time difference and thus having had, quote unquote, more time to develop?
So the gravitational field of the black hole is so weak by the time you get out here, it's not a thing.
It's just not a thing.
It's not a thing. So no, don't lose sleep over that.
Right.
And so, but what is interesting is, and this is like inside baseball here, but it turns out our speeds should be dropping off as you get out. So here's the whole galaxy, a flat disk spiral galaxy. As you get farther out, the speeds should be dropping off because you're farther away from the center of the action.
Okay.
But they're not. They're like stable.
Right.
They're, quote, flat. So our speed is the same, basically, as that of stars orbiting exterior to us. something is enabling that to happen. Something is having them go faster than they otherwise would.
Wow.
This was a discovery made in 1976 by Vera Rubin, and that was the discovery of dark matter in galaxies themselves.
Oh. So dark matter is actually
It's
influencing galaxies to the point
Yes,
where
our rotation rate.
our rotation rate should be slower at the
And the dark matter is giving it more gravity to turn.
wow.
Yeah. So
Now is that oh,
So all that means is that we have the same speed.
Exactly.
And so therefore there's not any relative anything. But even if we did start life at the same time, it could easily have life way sooner than we did or way later. Because every branch in the tree of life is an enormous contingency of events. Suppose the asteroid never took out the dinosaurs.
Right.
We would all still be, small rodents running underfoot trying to avoid being hors d'oeuvres for.
I'm going to say I'm trying to think of the dinosaur now.
T-Rex.
Thank you. But no, I wanted to go with the clever girl. That one.
Which one is that?
The raptor.
Oh, clever girl.
Velociraptor.
The Velociraptor.
The Velociraptor.
Clever. Yeah. I remember that line
Clever girl.
from Jurassic Park.
Right before he gets eaten.
By the way, you know how big those raptors actually are? They're about this big.
Oh, really? They're small.
Yeah, we have them on display.
Oh, in the museum.
So
They're
in the
tiny.
Well, yeah, I could kick it.
You could kick it.
I could totally bust his ass. So
That's so funny.
here I say I'm talking to a fossil.
Exactly. Yeah.
But they pumped him up for the movie.
Gotcha.
Yeah, just to make him a little more eye to eye.
Right,
You
exactly.
know, obviously something big can kill you, but something your size,
Right.
That's a little
fight.
more. That's a fight.
That's a fight.
That's a fight
now.
that you're going to lose,
That's
but it's a
right.
fight.
Yeah, it's still a fight.
Yeah, you think it's a fight, and then you're going to lose
Right,
anyway.
and then you get slashed open with the razor sharp talons of a velociraptor, and you're like, why did I bring a belly to a raptor fight? I don't know what I'm saying.
So the point is, almost anything, and we went 3 billion years with single-celled life.
Right.
If there's something else that pumped oxygen into the air faster than they did,
Right.
we would have had an oxygenated atmosphere much earlier, enabling oxygen metabolism life to take root sooner than it did on another planet, perhaps, rather than here.
Right.
If you want to use Earth as some kind of measure of things. So there could be life forms on planets just as old as ours that are 1 billion times more evolutionarily advanced than we are.
Right.
1 billion years.
That's funny.
Think about that.
That's great.
Oh, yeah.
That's pretty wild.
You got it.
All right.
Yeah, dude, I think that's it.
I know we're out of time. This was
Man, wait.
I
Stick your head in there. Tell me how many questions are
Let me
left.
see.
We lost Chuck.
All
so
right.
funny.
Well, thanks for tuning in. Nobody tunes anything anymore.
This is true.
Thanks for
Thanks for clicking on.
click. Yeah, whatever you did to hear this. Thanks for listening, watching. This has been Star Talk, Cosmic Queries Edition, Black Holes, and Dark Energy. Chuck Nice, always
Thank you.
good to have
Always
you.
a pleasure, brother.
All right. I'm Neil deGrasse Tyson, your personal astrophysicist, signing off from my office at the Hayden Planetarium, where I'm telling you, as I always do, to keep looking up. Chuck,
Yeah.
got yet another explainer. There's no end of these.
Good.
I kept
We
thinking,
need them.
will people get tired of them? I just don't know.
No, they're just increasing in popularity.
Yeah, well, there's a subject in the universe that no one grows tired of.
Oh.
The search for life, that's up there. But you know what I think is even higher than that?
Oh.
Black holes.
Oh, God, yes. People
God.
love black
People
holes.
love them some black holes.
Yeah.
And Jan 11 has been our go-to on this, but she comes to it as a physicist.
Yes.
So she can speak of black holes sort of in the abstract and the general relativity of them. But
and the blues music that they play.
the black hole blues, exactly.
Yeah, no,
but
no.
when a black hole shows up just in the house, in the astrophysicist house, I got to bring in an astrophysicist, black hole expert. Ooh. So let me introduce you to my friend and colleague, Savik Ford. Savik, welcome to Star Talk.
Hey, Neil and Chuck. Very lovely to be here. Thanks for having me.
Excellent. And so you are in the City University System of New York. Which campus is that?
I am at Borough of Manhattan Community College, BMCC.
Oh, okay. BMCC.
That's right.
Yeah.
Right in the
And-
thick of it.
And the Grad Center. So
And the Graduate Center.
I get around.
That's the CUNY Grad Center, CUNY
Correct.
Graduate Center. Excellent. And so last I checked, your research interests are what black holes are doing in the galaxy, as they eat stars, as stars orbit them, as they collide. So you're a black hole maven in the house. So
this day in black holes.
I am proud to claim that title. And for the record, black holes don't suck. They're awesome.
Oh, okay.
Okay.
All right. I got you.
Right.
I thought you were going to go where, what is it? There's no such thing as gravity. Earth sucks. You see? You ever hear that?
I don't know. It's where I keep all my stuff. I can't complain too bad.
So tell me, we checked recent news about a black hole that's just isolated with a whole trail of stars freshly born behind it, like just discovered, days ago. So Saba, who made this discovery?
The team was led by Peter Van Dockum at Yale.
Could you just tell me what that news story was and what the hell is going on in our backyard?
So it is very cool, and it's not super in our backyard. It's actually about 8 billion light years away.
Oh, wow.
Okay.
So it's
it's a day's trip.
Yeah. But
might want to pack a suitcase.
You could be gone for a while. But it's one of these supermassive black holes. So I am very interested we think that most galaxies have supermassive black holes in their centers. We know that ours has a supermassive black hole. It's about 4 million times the mass of our sun in the center of our galaxy. And that's like kind of a small one. Dang. So, yeah.
You're black hole envy, Chuck. It's been going on for a while.
I got to tell you, I do right now.
Yeah, even the Andromeda galaxy, the nearest big galaxy to us, what's its mass? What's the mass of its black hole?
It's a little closer to like 10 million times the mass of our sun. So, yeah, I know.
Man, let me tell you, that's embarrassing in the locker room. Go.
Right there, the same, right across the way. Right.
Yeah.
Okay.
Yeah.
So this one, did we get a mass on this one?
Yeah, so this is actually kind of in the Andromeda territory, maybe a little bit bigger, like 2 or 20 million times the mass of our sun.
Okay.
And so there's, and we think that there's actually the story that we've got is that there might be 3 black holes involved in this whole situation. So yeah.
3 distinct black holes that have not yet merged, but we're just observing them because we can't really observe them because there's no light.
Yes.
Okay.
Yes. And so basically, right, black holes give off no light. And so how do we observe them? And we have to rely on them influencing matter around them. And if that matter can give off light, then we can observe the influence of the black hole.
And
that's
infer the black
what
hole
we're doing.
from what it did to the light.
Exactly.
Okay. Mm-hmm.
Yes. Yeah. And that's generally like how we do these things. So this is like another example of it, but it's a very weird example. It was totally unexpected. The people who found it were not looking for it. They were looking at something else in the frame, and then they got this weird line, like straight line, which is not something you don't see a lot of straight lines in the universe. So they saw this really long straight line.
And just to be clear, this is evidence that we can discover things we're not looking for. Okay, because people wonder that, right? Do you have receptors for things you didn't ask a question about yet? The answer is yes, we do.
Yeah.
Sometimes science is like looking for your keys. It's like you lost your keys, you go looking for them, you're like, look at that, $20. Look at that. How great is that?
Yep. So that was totally what happened here. They were not looking for it. They were looking for other stuff. And they're like, whoa, $20. That's pretty great, guys. Mm-hmm. We've got this line, and lines are weird. So, anybody who's looking at a picture of galaxies in space and they see like a straight line across it, it's like, And that's a big thing, right? You don't have necessarily eureka moments. You have, that's weird moments. And so that's what happened here. These scientists were looking for something else entirely, and they saw this straight line, and it was really long and really thin. So it's about 40 kiloparsecs in length, which is about the width of our entire Milky Way galaxy.
Oh,
Okay.
Right. And so it's really
So about 100,000 light years. Yeah. Okay.
yeah, it's really long. And it's pointing back at this other galaxy that's a lot smaller than ours, which, it's been, it's 8 billion years old. So galaxies have grown in that time. They were smaller. It's pretty normal galaxy for the time that it was in, but it's small for modern galaxies. And they were trying to figure out what could cause a straight line. Sometimes we see jets that shoot out of supermassive black holes that live in the centers of galaxies, and they make straight lines. But this one, they looked at it in a lot of different wavelengths, and they were trying to figure out, well, if it was a jet, it should be spreading out as it goes away from the center of the galaxy. And they didn't see that kind of behavior. They also didn't see any evidence that it was an active galaxy, which was swallowing matter. So if black holes are going to shoot stuff out, that's usually while they're swallowing material. And there was no evidence of that. So they're like, what could this straight line thing be? It actually gets narrower the further away from the galaxy you go. And they realized when they were looking at it that if it was a jet, it should be giving off radio waves and X-rays, and it's not doing those things. But it looks like there's a lot of really bright young stars.
Wait, so these are those other wavelengths you said that they looked in and they didn't notice? Because if you just look at one wavelength, what do you know? You don't know anything, right? Until you see
exactly.
what else it's doing. Yeah.
Yeah. Mm-hmm. Yeah. You can't, it's like if you had like black and white photography, right? You can't always tell what's going on, but if you have like a color photograph, things really pop and you can learn a lot from that. So they basically went out and got a lot of X-rays and radio wave data. And besides that visible light, and they could tell that there were stars that are young, really young. And they realized that if a supermassive black hole had been shot out of the nucleus of the galaxy about 40 million years ago, then it could, as it's passing through the gas that surrounds that galaxy and every galaxy, it could cause little condensations of that gas that would collapse and form new stars. And it would do that like in a straight line because it's being shot out in a straight line. And so as it's going along, it's going to leave this trail of star formation behind it.
So a gas cloud minding its own business might not make stars. So it has to be perturbed in some way, such as the black hole passing through it, punching through it, I guess. Yeah.
It's kind of like if you've seen like those cool videos of like a bullet shooting through a gas, right? And it leaves that little turbulent wake behind it where it's got all of those like fun. And so that those turbulent chunks could then collapse and form new stars.
Okay. So I'm fine with this, but somewhere in there you said it got shot out of a galaxy.
Yeah, right? Like it's got shot out of a galaxy. So
can we go back to that right now, please?
It's 10 million times the mass of the sun. It got shot out of a galaxy. You don't just, that doesn't just like happen, right? So this is why you need 3 black holes for this to happen. So the basic idea is that when you have 2 galaxies that collide, they've each got a supermassive black hole in the middle, then the 2 black holes come together and they can form a binary supermassive black hole where they're orbiting around each other and they orbit really, really fast. If you were to have a 3rd galaxy come in and drop its supermassive black hole in, then you could get some kind of interaction, like a gravitational slingshot, and the binary could kick that 3rd object out. And this thing is actually, if this interpretation of this finding is correct, this thing is going at 1,600 kilometers a second.
So, Savik, how fast is that?
It would get you from the Earth to the moon in just a matter of minutes.
Well, it took the astronauts 3 days. So just for comparison, we're talking fast. All right.
Cruising.
All right. So this is the first of its kind that we've known.
Yes.
We love this.
This is definitely the first clear-cut example. And it's also very exciting because the binary black hole that should have been what was responsible for shooting out this one that's going on this straight line that they have observed, we won't necessarily see the binary, but it is in the right mass range that in the future we could detect it with gravitational waves. And so
if they collide with each other.
No, not if they collide with each other. So
just for existing.
Just as a binary.
Wow.
Because there's a space mission that's going to launch in 2034, LISA, the Laser Interferometric Gravitational Array, and it is built to detect binaries of like 10 million times the mass of the sun.
So I got it. Okay.
In gravitational waves.
LIGO was detecting black holes that are tens of times the mass of the sun.
Yes.
So the million times, that's a whole other detection regime.
Yeah, you need a totally different telescope, a totally different everything. So, and if you were to be much more than 10 million times the mass of the sun, you'd actually be too massive for LISA to see it. And so you would need even a different tactic. Okay. So this is really exciting that like we could point to this one and be like, we think there might be a binary right there.
So not everything in the universe feeds us in the wavelengths of our telescopes, of our chosen telescope. You got to meet the universe on its own grounds, in a sense. Is that a fair way to put it?
Yeah.
Yeah.
Well, so now part of me is thinking, Savick, part of me, this is just the antagonistic part of me is, well, they don't know what this thing is. So let's say 3 black holes made it. It's like, why not just say aliens did it? I mean, how frequent is a 3 black hole thing? Is this really a thing?
As frequent as black holes come home from college. They come home from college and the binary, which is the parents, are like, Trevor, listen, your mother and I have decided that you need to pay rent and we're gonna need to get $900 a month from you. And Trevor is like, for $900, I could get my own place. And the parents are like, exactly. Get out, Trevor.
Wait, Chuck, there's a very sensitive generation listening to you now about this very same issue.
You're absolutely right. I forgot. Yeah.
Don't
worry, kids. I'm not a homeowner either.
Wait, so Savick, so at what point do you reach for extraordinary explanations?
So there is, I would say this is not that extraordinary in the sense that a lot of people have suspected that there will be these systems of 3 black holes and 1 getting ejected.
And all you required was 3 galaxies for that, which we know surely has happened.
Yeah.
Definitely. Like we've got examples, like I can point to you for like, there's great Hubble images of like triple galaxy collisions. Like they happen all the time.
So Chuck, both of you in my lifetime, because Savick, I'm a little older than you, I was around when that cottage industry was born within modern astrophysics, just the study of merging galaxies. And it was called mergers and acquisitions. It was it was in the 80s
Wall
too.
Street 80s.
It was very 80s Wall Street, mergers and acquisitions.
Galaxies are good.
That's awesome.
The Gordon Gecko of the universe.
The more they eat, the better. Right.
Exactly.
That's good.
Yeah.
So all right. So I'm glad to hear that, because there are going to be people saying aliens did it, right? They have some black hole cannon or something.
Right? Yeah. There might be a guy we all know at some particular institution who might want to claim that, and the rest of us will laugh and say, that's just hobby. So.
All right. Well, Savick, thanks for this.
Yeah.
And just I'm delighted that you could bring this expertise to our explainer. Occasionally, our explainers do current events, and I like reaching out to my peeps out there. Well, again, Savick, thank you for that bit of expertise dropped into our weekly explainer.
Thank you for having me. Lovely.
And Chuck, always good to have you there, man.
Always a pleasure.
Neil deGrasse Tyson here, your personal astrophysicist. Keep looking up.